Okay, let's go ahead and get started. So just one administrative announcement. I decided we're about halfway through the semester. I've been giving you lots of problem sets, some of which have been hard, so I'm giving you a week off this week. Okay, so no problem set due next week. Actually, the week after that is well, it would be called spring break in other places, but we don't call it that here. So the next problems that I hand out, you'll actually have 2 weeks to do. So probably what I'll do, and one of those will be over break, and you won't have any classes over break, you won't have anything to do. So I might make it longer so you guys have something to do. Because I might even make it like a kind of mini project or something like that, where you work through a totally new aspect of quantum field theory that's slightly unrelated to stuff that I'll be talking about in class. I was thinking maybe finite temperature field theory or something like that. Or if I can, I might also just give you a few problems sort of developing non-abelian gauge theory, which is the subject that I'm going to start discussing today. And this is something that'll probably, just to sort of let you know where we are and where we're going, we're probably going to spend about 3 weeks discussing non-abelian gauge theories, which are the theories that describe the fundamental forces in the standard model of particle physics. And then from there we'll move on. I'll give maybe a brief discussion of anomalies, and I'll move on to spontaneous symmetry breaking, which will really set the stage for the introduction of the standard model. So I'm aiming by the end of this course for you to be able to write down precisely exactly the standard model of particle physics, understand every term in the action, understand its symmetries, understand its basic structure, and so forth. Although, of course, one could teach an entire course on the standard model of particle physics, and indeed, we have a course on the standard model of particle physics. So the last week, we'll say, of this class might be the first week of that class, or something like that. There might even be a little more overlap. But anyway, that's sort of the goal. But today, I just want to start by, before discussing non-abelian gauge theory, I wanted to remind you of something that we learned this fall when we discussed our theory of electromagnetism, quantum electrodynamics. In particular, what I'd like to do is start by just recalling how we formulate electromagnetism in terms of a so-called gauge principle. So the idea of the gauge principle in electromagnetism is the following. So let's imagine that we have a charged field, a field which has a global symmetry, such as a Dirac fermion, although I could just as easily talk about a complex scalar field. The Lagrangian of a Dirac fermion is rather simple. We've written it down many times. And the point is that this Lagrangian has a symmetry where we take psi and we rotate it, because psi is a complex number, by some phase e to the I theta. That's right, it's supposed to be a theta right there. And the point is that physical observables such as psi bar psi, which is the probability density or the particle number density, and psi bar gamma mu psi, which is the conserved current associated with this symmetry, are invariant when we take psi into e to the I theta psi. And indeed, because that's a symmetry of the Lagrangian, any interaction will respect this symmetry. So for example, we'll respect the conservation of the charge associated with this Noether current. So for example, the zero component of this current can be integrated to define a charge. That charge will be constant in time by Noether's theorem. In fact, however, these observables, and in particular these two particular observables that I have written down, are also invariant under the local version of this symmetry, where you take psi and you multiply it by a phase that now depends on your position in space or in space-time. And the idea that a global symmetry should be promoted to a local symmetry, namely one where the parameters of that symmetry are dependent on space-time, is really something that is natural if you think about it in the context of causality and special relativity. You know, if I'm here on Earth and I have this Dirac fermion and you're in Alpha Centauri 4 light years away, then there's no particular reason why I can't make a change of this global symmetry parameter theta independent of any change that you would make over an Alpha Centauri. Okay. So it's very natural to imagine promoting this global symmetry to a local symmetry. Okay. But the problem is that the physics is not invariant under this local symmetry. In particular, the Lagrangian is not invariant under the local symmetry. In particular, if you imagine taking psi to e to the I theta times psi, where theta is a function of position, how does the Lagrangian change? Well, you have an I d slash minus m times psi, so that becomes psi bar times e to the minus I theta I d slash minus m e to the plus I theta times psi. And what is that? Well, if theta were a constant, then of course this would be invariant. You could just pass it through the derivative. So that means that under this transformation, you get the initial action back again, plus a correction term where the derivative here hits that theta, so it brings down a factor of I, so you get minus psi bar psi, the scalar density, times I d slash theta. Okay. So the action is not invariant, and so interactions and physics will not respect this local symmetry that we've obtained by promoting the global symmetry to something that depends on space-time. Okay. So the question then is, can we modify the theory to make the action invariant? And the idea is the following. So the problem that we had here is the derivative did not commute or did not respect this local symmetry theta. And so you had a problem when that derivative hit the theta. So let's try and modify the derivative. So let's take d mu and replace it by something that we call the covariant derivative, which differs from the usual partial derivative by something that I'll call A. And if you like, this is the definition of A. It's the difference between the covariant derivative and the regular derivative. And A is constrained so that under the gauge transformation, you'll cancel that d slash theta term in the variation of the action. So in particular, what do we mean? We mean that when you take psi to e to the I theta psi, A is going to have to change in some way. So let's just say it goes to A plus delta A. And we're going to solve for delta A by demanding that under the transformation where psi goes to e to the I theta psi, the action is invariant even if theta is an arbitrary function of x. Okay? So in particular, let's just imagine our kinetic term now. So what is the kinetic term in the action? You have psi bar, well, it was I d slash minus m psi, but now the d slash has been replaced by, well, d mu has been replaced by d mu plus a mu, so you get d slash plus I a slash times psi. How does that term transform? Well, it goes to psi bar times I d slash plus I a slash times psi plus this term here. Okay, so that was minus psi bar psi I d slash theta. And then you have to add in the contribution coming from the variation of A under a gauge transformation. So what will that be? That'll be plus psi bar psi times, well, you have 2 I squared, so it's minus delta A slash. So these two terms must cancel. So that means that we have to set delta A mu to be minus d mu theta in order for the theory to be invariant under this local symmetry transformation. Everything clear so far? Okay. So what I've done here is I've derived the gauge transformation properties of the electromagnetic field by demanding that the global charge rotation of an electron should be promoted to some local symmetry. Any questions on that? No questions? Okay. So hopefully this is clear. The idea now is that A mu is some function of x and t, and so it should be able to have some dynamics. And so we should be able to regard A as a field then you can ask what kind of dynamics can it have if we think of A as a field. And we've learned that, well, if you want to study the dynamics of some field, then at low energy, you just start adding to the action every term you can, consistent with the symmetries of the theory. And if you want to study the infrared theory, then you should only consider those terms which are renormalizable, which give you, which correspond to relevant terms in the action of A. And so we should add to the action all terms that are consistent, that is to say, which are invariant under the gauge transformation. A mu goes to A mu minus d mu theta. So let's think about the sorts of terms that you could add. So, of course, we want an action which is quadratic in A. Otherwise, you would just shift A in order to make the action quadratic. The first term that you would think of is one that has no derivatives of A. The action has to be a scalar, and so the only quadratic thing you could write down is A mu, A mu. But this term is not invariant under the gauge transformation, so it's forbidden. In fact, if you start writing down derivatives of A, d mu A nu is also not invariant. The only thing you can write down, which is linear in derivatives and linear in A, is what we call the electromagnetic field strength, F mu nu, which is the antisymmetric combination of derivatives of A. And that's invariant under the gauge transformation, because if you look at the variation of this, the variation of A is d mu of A mu is d mu theta. So the variation of F mu nu is d mu d nu theta minus d nu d mu theta, which is equal to 0 by the equality of mixed partial derivatives. And this is the only invariant which is linear in A. The action, then, has to be a scalar. F mu nu is a tensor. And so the only action you can write down, consistent with the symmetries, gauge symmetry and Lorentz invariance, is the square of F mu nu. And then, of course, we would add to that the action of the electron coupled to the gauge field, where again, d mu is the usual derivative plus I A mu. Now, in principle, I could always choose my normalization of A to set the coefficient of this term to be whatever we like. So the typical normalization that we're going to use in this course is one where the gauge field is normalized so that we have a factor of 1 over 4 e squared here. This is sort of a, this is what we can think of as a geometric normalization of the gauge field. In particular, when we've chosen to normalize everything so that we have that factor of 1 over 4 e squared out front, we'll see that there's a sort of simple geometric interpretation of this gauge field. But of course, we could always rescale our gauge field to give you something that is a little more familiar from our earlier discussion of quantum electrodynamics. So a more canonical way of normalizing this field would be to define some canonically normalized A, which would be 1 over E times the A mu that I've defined above. In that case, that 1 over 4 e squared would just be a factor of a quarter. And the gauge transformation property, so under psi goes to E psi. So the gauge transformation then would pick up a relative factor of E. So for example, if you take psi to e to the I e theta psi and a mu to a mu minus d mu theta, then the action would be written in terms of a covariant derivative which has an E in it. Okay. So for example, I think in the fall when we studied quantum electrodynamics, we used what I've called the canonical normalization here. In that case, there is a factor of E here appearing in the gauge transformation and a factor of E appearing here. Okay. Of course, one could always rescale your parameter theta in some way. So for example, you could take theta to E times theta, and then there would be some 1 over E here. Okay, that's another sort of normalization that you could impose. But usually what we like to do is we like to put the coupling constant of electromagnetism here in the coefficient of F squared rather than in the coupling between A and psi bar psi. Is that clear? I mean, previously when we studied QED, we had the canonical normalization for the kinetic term of the photon, and the coupling constant E appeared as the coefficient of the a mu gamma psi bar gamma mu psi term. Here I've just rescaled E so that that coupling constant now disappears from that cubic interaction between a photon and two electrons, and it appears in the kinetic term instead. Obviously the physics can't care about that. It just makes some of my equations look a little simpler.
I have a question. So
Yes.
for these constants over there, they're like, say a critical value where this
So-
word becomes self-dual and anti-self.
So what constants are you referring to?
The one in front of A nu?
The one in front of, E?
Yeah.
Yeah, the electric charge? Yes. What's the question?
I was saying that does there exist critical value for like E, which this Lagrangian becomes self-dual and anti-self-dual?
What precisely do you mean by self-dual?
In the sense that if you write down the free energy function, we can write into the first Turing class plus some positive terms, and you reduce
Okay.
this to like Bogomolny equations. But this is the second one, right?
Yeah, I mean, okay. I mean, Bogomolny equations appear when you have supersymmetric theories, and
Yeah, like so-
this is not a supersymmetric theory, so I don't think that. I mean, yeah, I mean, I don't think, right now. Yeah, so I mean, I don't think that's going to be relevant here. Okay. Exactly. Yeah. I mean, okay. That's a little bit aside from what I was planning on talking about today. Okay, so one of the things that I promised is that with this normalization of A, we had a geometric interpretation of the gauge field. So in order to understand what I mean by that geometric interpretation, let's first just observe that we could rewrite F mu nu as the commutator of two covariant derivatives. So of course, two partial derivatives commute. That's the equality of mixed partial derivatives. But if you just take this definition here for d mu, so two partial derivatives, d by dx mu commute with one another. A mu commutes with A nu. So the only non-trivial term in that commutator is the commutator of d mu with A nu. Okay, d mu A nu minus A mu d nu, which is F mu nu. So F mu nu measures the failure of derivatives, covariant derivatives, to commute with one another. For those of you who've seen general relativity, this should not be a particularly surprising thing to think about. In that case, the covariant derivatives that one talks about are metric covariant derivatives, and the failure of two metric covariant derivatives to commute has a name. It's called the Riemann curvature, the curvature of space-time. And so what this means is that the electromagnetic field strength can, in some precise sense, be regarded as the curvature associated with this gauge field. So what I'd like to do now is introduce a slightly more geometric way of thinking about electromagnetism, that is to say, thinking about U1 gauge theory, which makes us all a little bit more explicit. And this will allow us to fairly easily generalize our considerations to other theories, which will lead us to non-abelian gauge theory. So in particular, what we'll see is that when we apply this procedure to theories with slightly more complicated global symmetries will naturally be led to slightly more complicated theories of gauge fields, which are Yang-Mills theories or non-abelian gauge theories. Question?
So
Yes.
the AUs are kind of like Christoffel symbols, but the
Correct.
compared phases at different points?
That's exactly what I'm going to be. That's exactly what we're going to discuss. So in this analogy where f mu nu is a curvature tensor, a mu plays the role of the Christoffel symbol, often referred to as the Christoffel connection. And so sometimes people refer to a mu as a connection. The point, really, as we'll see in a second, is that in general relativity, you think of a connection as something that you use to move vectors around. Okay. Here, we're not using the connection to move vectors around, but we're using it to move something simpler than vectors around. Okay. So really, electromagnetism is like a baby version of general relativity. And the geometric formulation of electromagnetism is much simpler than the geometric formulation of general relativity. Simple enough that you don't really have to think about it in terms of geometry, although it's much more helpful to do so, especially when you start thinking about non-abelian gauge theories. So how can we think about gauge theory geometrically? So let's just think about space-time. And space-time has a lot of points in it. Okay? But let's just think of a very simple model of space-time as a lattice of points. If we were thinking about, say, some material where you have atoms on a lattice, then you literally think of space-time as a lattice of points, one for each atomic site. But more generally, this is some pretty good approximation to what we mean by space-time. And so we have a bunch of points here, and you have the value of the field at each point. So that, for example, would be psi of x. Right there, where x is some vector. The value of the field at this point would be psi of x plus epsilon, where epsilon is the spacing between those 2 points. And if you want to think about this a little bit more carefully, you might put an index here, so that'd be psi of x mu. This would be psi of x mu plus epsilon mu, where epsilon mu is this vector right here. And at this point here, the field would be psi of x mu plus 2 epsilon mu, and so on and so forth. And just to make my life simple, instead of considering a Dirac field, where psi had some complicated spinor indices, which we would have to think about, let's just consider a complex scalar field. That's also a theory that has a U1 symmetry. We used it when we studied scalar quantum electrodynamics. It's the same U1 symmetry. It was the field goes to e to the I theta times the field. So I'll just let psi be a complex scalar. And so psi, the field then, is described by a complex scalar for each point in space-time. And if you want, you should really think about this as an absolute value of psi times a phase. So alpha is the argument of psi. And so we want to think of alpha as living on a circle and there's a circle at each space-time point. When you think about the possible set of field values, let's forget about the absolute value of psi. The important point is the phase. And there's one value of a phase for each point in space-time. And the gauge symmetry, let's first actually think about the global symmetry, where theta is just a constant. Psi to e to the I theta psi just rotates this circle. So it takes alpha to alpha plus theta. Now, derivative. So we have to construct the action for our field using derivatives. Well, in this sort of way of thinking of space-time as a lattice, a derivative would be written as something like this. So if epsilon mu is a little vector that tells us about the displacement between 2 points, then the derivative of psi in the direction epsilon mu is, in the limit where epsilon is small, psi at x minus psi at x plus epsilon divided by epsilon. So here I'm being a little sloppy with my indices here. So the absolute value of epsilon is the length of the vector epsilon. And I've left off my indices on x and epsilon there. So this is just really the definition of the derivative. But if you think about space-time as a lattice, you see that this derivative requires us to compare fields, or to compare values of the field at neighboring points in space-time. And what is the covariant derivative? The covariant derivative is just a different way of comparing neighboring points. So in particular, remember that we have a circle at each point in space-time. So if you have one point here, then you have a little circle. Okay, let's draw the circle around some axes like that. Okay. So there's your circle at point x. And here's your circle at point x plus epsilon. And if you think naively, you might want to just declare that this point over here on that circle is the same as this point over here on that circle. But you could also choose to, say, rotate the circle by pi over 2 when you make this comparison. So that, in fact, this point right here would map to this point right here. Okay, so you might have some relative rotation by some angle when you compare these two different points. And A mu is nothing more and nothing less than some instruction for how you should be comparing different points in space-time. So each A mu is an instruction for how to compare or connect neighboring points. And this is why A mu is sometimes referred to as a connection. And the process by which psi is moved from one point to another using the connection A mu is known as parallel transport. And it's often called parallel transport with respect to a given connection A mu. So that's the kind of basic picture. There's some fancy mathematics that people sometimes use to describe this. People say that, you would say that A mu is, that psi is described by some line bundle, and the connection is some, covariant derivative that respects the structure of this line bundle. But really, it's just a very simple picture where you have a circle at each point in space-time, and A mu is allowing you to compare different neighboring points by rotating the circle in some way. And all non-abelian gauge theory is you replace the circle by something slightly more different, something slightly more sophisticated. Okay? You could replace it by a sphere, and you could compare using a rotation on the two-sphere. For example, if you wanted to get an SU2 gauge theory, as opposed to just a rotation on a circle if you wanted to get the U1 gauge theory or electromagnetism. So what I'd like to do now is just give you some formulas to make that all a little bit more concrete, but maybe before I do so, I should pause and see if there are any questions. So if you wanted to think about differential geometry in this language, that is to say general relativity, then the connection, that is the Christoffel connection or the metric covariant derivative in general relativity, is something that allows you to take a vector at one point and compare it to a vector at a neighboring point. And so there, the relevant transformation is not a rotation on a circle, but it's some sort of, what you would call an orthogonal transformation on the tangent space at a point, the space of vectors. Indeed, the language that we use to describe general relativity is very, very similar to that which we use to describe non-abelian gauge theories. There's a sense in which general relativity is a kind of gauge theory. Yes? Question?
Here we have a transformation in the fields, right? After the derivatives.
Yes. That's correct. That's correct. Yeah. I mean, I didn't say that general relativity was exactly like a gauge theory. It's a very close analogy, though. I mean, to some extent, what you call a field variable and what you call a space-time variable depends on how you think about it. But let's not get into that. Other questions? Yes.
Yeah, I think it's called like a Wilson line. Is that
Yeah, we're gonna. That's the next. That's what I'm going to write down next. Okay. Yes. Good question. Okay. Why don't I talk about a Wilson line and then we'll introduce it next. Okay. So how exactly is it that we're using the gauge field to compare different points? Well, the covariant derivative is d mu plus the covariant derivative is d mu plus I a mu. So in this discrete model, the way that we use a gauge field a mu to compare different points is that we take the value of the field at a given point x and we multiply by a phase that is usually called the Wilson line U, so that let's say that we have 2 points in space-time. So if we have a point x here and some other point y here, then you need to specify a curve that connects the two. In the case above, where we were considering lattice points separated by a very small difference, this might be the point x and the point y would be x plus epsilon. But more generally, you get a phase that depends on both the points x and y, as well as the curve that you choose that connects the two. And it's given by the integral of A along the curve, from the point x to point y. So that may not be obvious to you, but I'm going to do a couple calculations in a second, which should make it clear precisely why this has to be the right phase. And this phase is known as a Wilson line. So if I were working in the language of vector calculus instead of using my 4-vector notation, this would be the integral of A dotted with dx, along some line. So remember, when you have A mu has a lowered index, so it's a 1 form, and what objects with 1 index are integrated for a living. That's what they do for a living. So if you see an object with 1 index, then you should be looking for something to integrate it along to get a number. That's that's what vectors do for a living. Really, that's what 1 forms do for a living, which are objects with 1 lower index. Okay. So why exactly is this the correct prescription? So the idea is that under a local gauge transformation, you could take the field psi at a point x, and it will go to e to the I theta of x times psi of x. And you could also consider psi at the point y, which will pick up a different factor, theta of y times psi of y. And then we could ask how it is the Wilson line will transform under this gauge transformation. Well, remember, A picks up a factor of the derivative of theta. And so you can then use, well, the fundamental theorem of calculus to note that the integral from x to y of d by dx mu d theta dx mu is theta of y minus theta of x. So the Wilson line is e to the I, well, okay, theta of y. Okay, I should have really put a minus sign there, so that I'll get a minus sign there, u of yx, times e to the I theta of x. Sorry, no minus sign there. Oh, but there's a minus sign in the, yes. Sorry, there is a minus sign there because there was a minus sign. So remember that a mu goes to a mu minus d mu theta. So using the fundamental theorem of calculus and our definition of the Wilson line, u of y will pick up an e to the I theta y minus I theta x. Okay. So what does that mean? That means, so the Wilson line u is some phase. So you could take psi at the point x and multiply it by the phase u of yx. And how would that transform under a gauge transformation? It would pick up an e to the I theta y times u of yx psi of x. So the point is that if you take psi of x, you multiply it by the Wilson line that connects x to y, then you get an object that transforms just like psi of y. And that's really the point. The point is that in a gauge theory, if you have a local symmetry, psi can pick up a different factor at each point, and the Wilson line is just the gadget that allows you to take psi at some point x and move it to some other point y, consistent with the gauge symmetry. Yes?
So why is this Wilson line independent of which line you're integrating?
No, as I said, it depends on which line you integrate
So
it
you
on.
pick the line.
Yes. So as I said, it depends on your choice of curve here. That's very important. That's actually the next thing that we're going to study. So yes, that's an important point. So the important thing to note is that u of yx, although my notation, it's sort of implicit, I haven't said it explicitly, depends on the choice of curve between x and y. And only in special cases will it actually be independent of that curve. So this is what parallel transport is. You know, you fix an A, then you integrate the A up along all possible curves to define this Wilson line, and then that allows you to transport psi from one point to another. Good. Any questions on this? Yes.
I have a question. Would this be like a recent password?
Oh, yeah, you want an sure, we can take an intermission. Okay, good. Here, let me pause this. Okay, good. Let's keep going. So, the question that we have now, so we have, given a gauge field A, we have the geometric interpretation in terms of the Wilson line, which is this operator that allows us to parallel transport things along curves. what then is the curvature? What then is the meaning of the field strength? The point is that the field strength, which is the commutator of the covariant derivative, is then a measurement of the failure of the parallel transport operation to bring a field back to itself when you transport around a closed loop. So in particular, F mu nu at a point describes the failure of psi to come back to itself when we transport it around a very small closed loop at a given point in space. The value of F mu nu at a point in space can be thought of as the infinitesimal change, the change in psi, in our field psi, as we transport it around a little tiny loop according to this parallel transport operation. So let's see that. So let's imagine that you have your field at some point. Let's call that point x. And let's imagine that we transport it to some other point, which is going to be very close by. And then we want to transport it around some closed loop. So then we're going to go off in some other direction, then transport back, and then down again. Okay. So we want to transport in some closed loop. And so let's call this vector here a mu, and this vector here b mu. Those are two vectors that characterize this little tiny square around which we're transporting our field. Oh yes, b should be pointing in the other direction. Yes. Good.
Sorry, can I-
Yes.
What's the space that we make out of it?
Space. This is space. The space is just space. It's space. X is a point in space. Space-time. Yeah, space-time. Call it space-time. Yeah. Or think in Euclidean. Yeah, it's space. Space is space. Or space-time. I'm not being very precise. Yes, it's space-time. Space-time. Just call it space-time. Okay, good. So what is the what's the Wilson line associated with that small closed loop? Well, let's see. I've arranged my arrows. So the way that my notation for the Wilson line is that the end point was the first argument and the beginning point was the second argument. So we could write this as u at x plus a mu, x plus a mu, and then u at x plus a mu, x plus a mu plus b mu. Okay, I should want to be careful, write down all my indices here. Then a u from x plus a mu plus b mu to x plus b. And then finally a u from x plus b back to x again. So I just need to multiply these four Wilson line operators together. Okay, and this is a very, very small loop. So when I perform this integral along the line, I don't actually need to integrate. So I can use the fact that the integral of a mu dx mu, say, from the point, I don't know, x to x plus a, where a is some vector, is in the limit where that line is very short, just given by a mu contracted, so the vector a mu contracted with the field a mu. And if you want to be super precise, I should really, I should really evaluate a mu at the midpoint between those two. So at x plus a over 2. because strictly speaking, the derivative at a point, the best way of approximating it is by taking the derivative of f of x is f of x minus epsilon minus f of x plus epsilon divided by 2 epsilon. So what do you get? You get the integral of I. So from that first term, what will you get? You'll get a mu at x plus a over 2, just neglecting those. Here, I'm going to pull out an overall factor of I to make life simpler. So you'll get a mu at x plus a over 2, contracted with little a mu. And then from the next term, you'll get a mu at, what is that going to be? X plus a plus b over 2, contracted with b mu. For that third guy, we're subtracting off an a, so you'll get minus a mu at x plus b plus a over 2, contracted with a mu, minus a mu at x plus b over 2, the midpoint of that final line, times b mu. So let's just stare at that for a second. So the first thing that you should notice is that, well, let's compare this term here to this term here. B is very small when we compare those two terms. So you could write that term as a mu b nu times the derivative with respect to x nu of a mu. Evaluated at the point x plus a over 2. And similarly, this second term here is if I've done everything correctly. So let's compare this second term to this third term. So that's going to be, oh, actually I got a minus sign wrong. Okay, so this first term, yeah, you need to be a little careful about this. That first term is actually minus this, because here you have an x plus b, so f of x plus b minus f of x over b is the derivative of f. And so so here you have an overall minus sign, which is that minus sign, and then you have plus a nu b mu times the derivative of x of a mu. And strictly speaking, we're calculating the derivatives of a at different points. In the first case, I'm calculating it at the point x plus a over 2, or actually I suppose really if you think about it precisely, we're computing both of those derivatives at x plus a over 2 plus b over 2. So in any case, comparisons of the point at which you're taking the derivative can be neglected in the limit where these points are very close. And so in the limit where the square is very small, this Wilson line, which we would now call a Wilson loop because it's a closed loop, is the exponential of I times a mu b nu f mu nu. Okay. Now, I've made some approximations here by taking this a very small loop and things like that. So an exercise which I challenge you to do for yourselves is to generalize this to finite loops using an appropriate version, a four-dimensional version of Stokes' theorem. Or maybe it's Green's theorem. I can never remember what the difference is between the two. It's the general. It'll be the generalized Stokes theorem. Yeah. Okay. If you've seen differential forms, how many of you have seen differential forms? If you've seen differential forms, that'll be very easy. If you haven't, you should learn differential forms. They're really nice. Okay. So, the curvature F, the field strength F, is a measurement of the failure of a Wilson loop to vanish. Okay, so this is a geometric description of electromagnetism. In the case of electromagnetism, this geometric description in terms of, well, what we might call connections and curvatures and what people call line bundles and stuff like that is kind of overkill. It's like, you know, using a sledgehammer to open a walnut or something like that. But when we talk about more complicated theories, really this geometric description, I think, is the easiest way to think about the theory. Okay. So what I'd now like to do is consider non-abelian gauge theory, that is to say Yang-Mills theory, constructed from this geometric point of view. So the construction of Yang-Mills theory is really exactly the same as the construction of electromagnetism, where we invoke this gauge principle that all of our symmetries have to be promoted to local symmetries. The only difference being that we now consider not just one kind of electron, but with multiple kinds of electron. So it's the same thing, except we have more complicated fields. So in particular, we now imagine that, so previously we had one Dirac spinner describing the electron. Now let's imagine that we have n Dirac spinners labeled by an index. Oh, I won't call it A. People usually use that for something else. I'll label it by an index I, where I runs from 1 up to n. So for example, n could be equal to 3. And we might, if n is equal to 3, you might want to represent these 3 Dirac spinners in a column vector with 3 entries. You might even give name to these 3 different kinds of spinners. You might call the 3 indices not 1, 2, and 3, but red, green, and blue, or something like that. Okay. So for example, that is what we would use if we wanted to describe quantum chromodynamics, which is the theory of quarks, which are labeled by 3 colors, which is just an index on our spinor field. And then the Lagrangian will again be given by psi bar I d slash minus m psi, where here now psi is a 3-component column vector, each one of which is a 4-component Dirac spinner. And psi bar is now a 3-component column vector, each of which is a 4-component Dirac spinner. But of course now it's a barred spinner, so if you wanted to write out the Dirac index, then it would be a 4-component column vector as well. This is why we usually don't write things out in terms of column vectors and row vectors, because you have column vectors inside row vectors, and it gets very complicated. That's why we tend to use a more abstract index notation, or an even more abstract notation where we don't write the indices at all. Yes, question?
So now the order isn't reversed when
Sorry, the order...
we have sidebar and one is reversed order.
Yes. I'm not reversing the order. No, this is just a vanilla, yes, this is a vanilla bar. We could call it an, yeah. That's right, that's right. I've written it exactly as I meant to. So we could also just write, if we wanted to write this a little more prosaically, we could just write L as psi bar I d slash minus m psi j delta ij. Or here, I guess I used a lower index, so I'll put lower indices here. If you wanted to use not a matrix notation, but a sort of index notation. Is that clear? Good. And what's the point? The point is that this is now invariant under a larger symmetry group than the one that was relevant for electromagnetism. In particular, you can take psi, now thinking of it as a n-dimensional vector, and multiply it by v psi, where v is a complex n by n matrix. Now it's important, I'm multiplying the index in the n-dimensional space, not in the 4-component Dirac spinor space. So really, if you wanted to write that out in component notation, psi I goes to Vij psi j, using summation notation. Yes?
So this Vij is that number, it's not
Well, it's n squared numbers, right?
no, the Vij by itself.
Oh, Vij is a number, yes.
It's not
Yeah,
a
Vij is a complex number. That's
It's not
correct.
a
That's correct, yeah. So there's different symmetry. There's the space-time Lorentz invariance, which acts on the Dirac spinor, which we call alpha. Usually we call them alpha, or sometimes dotted spinors, A and B and stuff like that. And V acts on this global symmetry index, which I've called I here. And never the twain shall meet. Okay. Question?
Yeah, but why, well, if we take the bigger symmetry, why it breaks down into this and the original electromagnetic?
Yes, that is an excellent question. You could ask, is it possible to mix these different kinds of symmetries? And there are actually theorems that you cannot construct interacting theories, non-trivial interacting theories, where the space-time symmetries mix with the gauge symmetries. That's, I believe that's the Weinberg-Witten theorem. It's a kind of deep result in quantum field theory. There are ways that people can get around. You can get around this in some cases, but generally speaking, theories. It's impossible to write down non-trivial interacting theories like that. That said, given the fact that you can think about gauge symmetries geometrically, and you can think about space-time geometrically, it's very tempting to try and come up with a common language where some of these are treated on equal footing. There are cases where that does happen, but for now, so for relatively simple theories like this, our global symmetry and gauge symmetry indices aren't going to talk to our space-time indices. There are all kinds of things that one can do where these things will talk to each other in one way or another. Good. Other questions? Coleman-Mandula, sorry. Weinberg-Witten is the higher spin. Yes. Sorry, yeah, Weinberg-Witten is a different theorem. Coleman-Mandula theorem, thank you. Which is wrong, by the way. Okay. But it's wrong in a very interesting way, which led to the discovery of supersymmetry. Okay, good. Okay, so importantly, under this symmetry, psi goes to v psi, and psi bar goes to psi bar times v dagger. So that means that in order to preserve the Lagrangian, v must obey v dagger v is equal to 1. So that the Lagrangian, so for example, the mass term is psi bar psi, which goes to psi bar v dagger v times psi, which will be equal to psi bar psi if v dagger v is equal to 1. And so this means that v is a unitary n by n matrix. And we call this the group of all unitary n by n matrices Un. And typically, we're going to restrict our attention to cases where the determinant of V is equal to 1. So it's sort of the reason being that in the group of n by n unitary matrices, there's an overall phase out front that just acts like a U1, just like electromagnetism. But the kind of new part, the non-trivial part, is the part where the determinant of V is equal to 1. So the set of all V in Un, whose determinant is equal to 1, is a group that's referred to as SUN, which is the group of special unitary matrices. Specially referring to the fact that the determinant is equal to 1. And what we would like to do is now make this symmetry local. The gauge principle instructs us to promote this symmetry to a local symmetry where now the parameters of our transformation, which were this n by n matrix V, now becomes functions of our point in space. So psi goes to V of x times psi. So whereas previously for our local symmetry, V was a collection of n squared complex numbers, now it's a collection of n squared complex fields. And in order for this to work, just as in the case of a electromagnetism, what you need is a connection that allows us to compare fields at different points. So in particular, what we need is a U of x. We need a Wilson line operator, U of y and x, which has the property that under a gauge transformation, where psi goes to V of x times psi, U of yx will go to V of y, U of yx, V of x dagger, so that, sorry, this is supposed to be psi of x, so that if you take this Wilson line operator and you multiply it times psi of x, you get something that transforms as if it lives at the point y. Yes?
Just before you moved on, when you defined the special unitary group,
Mm-hmm.
you started with an element of SUN with the specification that equals 1, and just UN with that extra specification.
Oh, I'm sorry. Thank you about that. Thank you. Sorry about that. Good. Sorry. Hopefully that was more or less clear. Okay. Good. Questions so far? So clearly, in order for this transformation, for this connection U to transform in this way that I've written here, U must be an n by n matrix, just like V. And what I would like to do is understand how everything works a little bit more infinitesimally by expanding everything when the points y and x are very close to one another. So far I've written down everything at the level of finite transformations between points x and y that are very far apart. So what happens if we expand infinitesimally? Okay. And in order to do that, I'm going to need to introduce a little bit of group theory. So in order to expand infinitesimally, what we want to use is the fact that every unitary matrix, V, can be expanded as an exponential. So V, any unitary matrix V, can be written as the exponential of I theta A T A, where the theta A's are some numbers some real numbers and the TA's are complex n by n matrices. And here, and in the index A, well, strictly speaking, it runs from 1 up to n squared, but actually it runs slightly lower than that because there aren't quite as many independent matrices. It runs from 1 to n times n plus 1 over 2. So the TAs have a name. They're known as the generators of the SUN Lie algebra. So a couple comments about the notation are in order. So A here is an index that runs from 1 up to n times n plus 1 over 2. I'm summing over A here, okay? I'm not using the Einstein summation notation because I have my repeated indices are being summed over, but I'm not being careful to have one upper and one lower index. For some reason, this is the standard notation when people talk about Lie algebra indices. It sort of hurts me a little bit, but that's just the standard notation, and so I'm going to stick with it. One comment that I'll make is that A here is so n times n plus 1 over 2 is the dimension of SUN, it is the number of continuous parameters that one has to specify in order to uniquely specify an element of the group SUN. The other piece of notation that I should mention is that very often people use a slightly different notation to distinguish the group SUN from the algebra of the matrices SUN. So people will often use capital SU for the group and lowercase su for the algebra. So if it wasn't already apparent, those are lowercase letters right there. Now, the first thing to notice is that because V dagger V is equal to 1, that implies that the T's are Hermitian matrices. Okay. That's easy to check. All you do is take the dagger of this expression here, use the fact that the thetas are real, and you get a minus sign from the i's, and then the T's are Hermitian matrices. If we hadn't put that factor of I in there, then we get the same thing, but the T's would be anti-Hermitian. To first approximation, the difference between a physicist and a mathematician is a physicist is someone who thinks that the generators of a Lie algebra are Hermitian, and a mathematician will think something else. Okay? Yeah. Okay. And the idea is that the group multiplication law for SUN then implies some sort of multiplication law for the Lie algebra matrices that I called TA. So how can we see that? Well, that really is the Campbell-Baker-Hausdorff lemma. So the idea is that if you have some group multiplication law, say that two SUN matrices multiply to give you a third SUN matrix, you can just write that out. You get an e to the I theta A1 TA, e to the I theta A1 TA is equal, sorry, theta 2A is equal to e to the I theta 3A TA, where theta 1, theta 2, and theta 3 are three sets of n times n plus 1 over 2 real numbers that specify a SUN matrix. And then you just Campbell-Baker-Hausdorffize this formula right here. And what do you get? You get the exponential, so the leading term. So let's just take the approximation where the thetas are all very small. So the leading term is I times theta A1 plus theta A2 times TA. And then the next term, the next term comes, so Campbell-Baker-Hausdorff is e to the A, e to the B, is e to the A plus B plus 1/2 commutator of AB plus terms that you never need. And so we need to take the commutator of those two terms, so you get a minus 1/2 times theta 1A, theta 2B, commutator of TA with TB. Plus dot, dot, dot. And that has to be equal to this guy for some theta 3. So what does that mean? That means that there must be some formula where the commutator of the t's is equal to another t. So with a factor of I there, if we want our FABCs to be real. So there are going to be some numbers FABC that have the property that the commutator of two of the t's is equal to a third t. And these FABCs are known as the structure constants of the Lie algebra SUN. Okay. So unfortunately I'm out of time here, but it's probably worth just mentioning that there's one very simple example that you know quite well. So for example, SU2, which is the gauge theory that describes the electroweak force. In this case, the TAs have a name. They're the Pauli matrices. And the structure constants are given by the epsilon symbol, epsilon ijk. Any questions on this? So next time what I'm going to do is use the gauge principle in order to understand what local field I must introduce in order to have local symmetry under these SUN transformations. And then I'll use invariance under the gauge symmetry and special relativity to write down the action. So we'll construct, just purely from symmetry considerations, the action of Yang-Mills theory. Yes?
So I understand that for a U1 gauge theory, then you can expect that to be able to rotate the fields at different points in the space-time. It wouldn't affect any embeddings. But if you have multiple fields and you rotate them into each other, why
Yes.
should that be?
Well, let's put it this way. Let's say that I have two fields. Okay. let's call them, okay, I don't know. Let's call them fields psi1 and psi2. Okay. And over here, there's a symmetry, which says that I can't distinguish between psi1 and psi2. And in Alpha Centauri, there's that same symmetry. Then what I call the first field, I might change the identification between those two fields here in a different way from how I did in Alpha Centauri. I mean, if you like, the picture that you want to have in mind, so previously we had a circle at each point in space, and the gauge transformations were rotations on that circle. Here, what we're going to have in the case of two fields is you really have, well, a complex two-plane, or if you want to think about it, well, I guess you could think about it as a complex two-plane for each point in space. And then what you're doing is you're multiplying the coordinates of that complex two-plane, namely the one where our field variables are living in, by some unitary 2x2 matrix at each point in space. I'm not sure if I'm like...
So the fields have to be like indistinguishable.
That's right. That's right. I mean, if you take our quark example, like let's say we have three species of quark: red quark, blue quark, green quark. Okay. Then over here, what you call a red quark might not be the same as what someone in Alpha Centauri calls a red quark. But the fact that you have this symmetry, where you can't tell the difference between red quarks, blue quarks, and green quarks, it's very hard to say that, means that it shouldn't matter if the person in Alpha Centauri has, if you change your labeling of the quarks, and sort of because of locality and causality, it shouldn't matter if someone in Alpha Centauri chooses a different label for the red, blue, and green quarks. What they call a red quark, I call a blue quark, but can't matter. Good. Any other questions? How much of this geometry have you seen? Have you guys done? You haven't done any of this geometry, like connections or line bundles or anything like that. You guys haven't seen any of that. Okay. It's sort of a mathy terminology that you don't really need to pay too much attention to, but I think it is useful for understanding a little bit more based on symmetries, why it is gauge theories have the form that they do. I could have started our introduction to gauge theories by writing down an action and just telling you to compute, but I think this is maybe a more intuitive way of understanding where gauge theories come from. Okay, I will see you on Tuesday.